In today's video, we're going to be talking about section 2.8, combining, and I always miss an IN in there, combining functions and composite functions. And so I'll talk about combining functions first, and then we'll come back to composite functions. And this is where we want to talk about, well, what if we have some function f of x, and we want to add another function g of x to it? Or if we have some function x, and we want to add a function, or subtract a g of x. Or maybe we have an f of x, and we want to multiply it by a g of x. Or we want to take an f of x and divide it by a g of x. Well, these are all of our definitions for our combining functions. So we have our sum of two functions, which we write as f plus g of x. Our difference of two functions, f minus g of x. F times g of x as our product, and f over g of x, which is our quotient. And by definition, f plus g of x is just f of that x plus g of that x. F minus g of x is just f of that x minus g of that x. And it's important to note that the domain of any of these functions is x in the domain of f and x in the domain of g both. So it has to be in both. The only exception, and I'll pick another color for that, here we exclude x where g of x equals 0, right? Because we can't divide by 0. So our domain will be the x values for which f is defined and g is defined, unless we're looking at our quotient, and then we also exclude those where g of x is equal to 0. So let's go ahead and look at this example. Here we have f of x on the left and g of x on the right. And the directions I'll give for this are find f plus g of x at 2, f minus g at negative 1, f times g at negative 2, f over g at negative 3, and f over g at 1. And so, picking a different color I haven't used before, we'll go with light blue. F plus g at 2, by definition on our previous slide, is f of 2 plus g of 2. So we look at our graph, 1, 2 is negative 2, and g of 2 is 1, 2, negative 1. So the sum is negative 3. F minus g at negative 1 is just f of negative 1 minus g of negative 1. F of minus 1 is 1. G of minus 1 is negative 1, 2, 3, 4. 1 minus negative 4, which is 1 plus 4, or 5. F times g of, that was supposed to be a negative 2, is just f of negative 2 times g of negative 2. F of negative 2, go left 2, that's 1 times g of negative 2, 1, 2, is at 2. 1 times 2 is 2. F over g at negative 3, well, f of negative 3 is 1, 2, 3, 1, and g at 1, 2, 3 is 0. Skip it. Negative 3 isn't in the domain. Remember, we exclude whenever g of x equals 0 because g of negative 3 is 0. And so now f over g of 1 is negative 2 over g at 1 is also negative 2. And we get 1. Right, and so this is as easy as extracting the values from a graph and then finding them from each point and substituting them. But what if we don't have a graph? And particularly, what if we don't have a weird piecewise function like this? Well, let's consider another example. Suppose we have example. Let f of x be x over x squared minus 6x plus 8, and g of x be 3 minus x. And it's going to say find f plus g of negative 1, f minus g of 0, f times g at 2, and f over g at 1. But let's always begin by finding our domains. So the domain, and let me pick a different color. The domain of f is only going to be when that denominator is 0. So let's see. We have two numbers that multiply by 8 to give us negative 6. We can have x minus 4, x minus 2. That looks good to me. And so that's when x can't be 2 or 4. So we have negative infinity to 2, 2 to 4, 4 to infinity. And then our domain of g is just all real numbers. So we know automatically that we can evaluate our functions when x equals 2 or when x equals 4. So f plus g of negative 1, well, that's f of 1. Let me pick a different color. F of 1 plus f of negative 1 plus g of negative 1. And actually, I'm going to remove these because I think we're going to run out of space. So f of 1, or f of negative 1, excuse me, negative 1 over negative 1 squared minus 6 times negative 1 plus 8 plus 3 minus negative 1. Negative 1 over 1 squared is 1. Negative 6 times negative 1 is plus 6 plus 8 plus 3 minus minus is plus 4. Negative 1 over 6 and 8 is 14, 15. Negative 1 15th plus 4. That's 3 and 14 15ths. 15, 30, 45, 55, 59, 15ths. Is f of g, so f plus g at negative 1 is 59 15ths. Alright, so we're going to use these same f and g values, but we're going to go on to f minus g at 0. Well, that's just 0 over 0 squared minus 6 times 0 plus 8 minus, and put a big bracket so we make sure we remember to distribute our negative, 3 minus 0. Well, 0 over anything, 0 over 8 is 0, minus 3, negative 3. And then we can look at f times g of 2. So we have, again, let's go ahead and put some big brackets so we don't lose the track. Plugging in a 2, we have 2 over 2 squared minus 6 times 2 plus 8 times 3 minus 2. 2 over 2 squared is 4. Minus 12 is negative 8 plus 8 is 0. We get 2 over 0. What does that show us? Let's go back. What was our domain? X naught 2, X naught 4. So here we have that this is undefined. X equals 2 is not in the domain. Switch back to green. We'll do one more example. F over G of 1. So here we have, remind us over here, f of x equals x over, what was it, x minus 4, x minus 2. And g of x, we had 3 minus x. So here we get a big fraction bar. 1 over 1 minus 4, 1 minus 2, over 3 minus 1. And then we have 1 over negative 3 times negative 1 over 2. Negative 3 times negative 1 is 3. 1 over 3 over 2. And so we can multiply the top and the bottom by a half. It's 1, 1/6. So f over g of 1 is 1/6. But remember, whenever we define, and I'll use red, we have to exclude x where g of x equals 0. So 3 minus x equals 0 when x equals 3. So here, the domain of f over g of x is, so we already had to exclude negative 2 and, or we had to exclude 2 and 4 because of f of x. And so our domain is negative infinity to 2. But now we have to exclude 3. It's from 2 to 3. And then 3 to 4. 4 to infinity. And whenever we write set notation like that, it gets a little cumbersome. You can also write the reals minus the set containing 2, 3, and 4. So both of those are valid ways to write the domain of f over g. Now, that more or less covers this notion of combining functions. We can add, subtract, multiply, and divide functions, but we have to be careful when we divide by a g of x. G of x can't be 0. And so now that we've covered that part, we can move on to composition. Composition of functions. This is where we're going to talk about not some f of x and a g of x, but we're going to look at nesting a g of x inside. And so we'll read this as f composed with g of x, or we can say f of g of x. And our shorthand for f of g of x is f composed with g of x. And so that's a little circle. And so f composed with g of x is by definition, and that's what that little triangle means, f of g of x. Some people will call this fog, but that's on O. It's a little circle. And it's different than our multiplies circle. So let's go ahead and consider an example. If f of x equals the square root of x and g of x equals x squared minus 1, I want us to picture f composed with g of x this way. F composed with g of x is. Now let me go ahead. I'm going to draw some things that maybe won't make sense at first, but we'll get there. All right. These are like kind of black boxes that have functions inside. I guess they're not black boxes, they're magenta boxes. And here we have our input. And remember, f composed with g of x is f of g of x. And so we need to find g of x and substitute that into f. So we have some input x that goes through the process g of x. And we said g of x was x squared minus 1. So when we go through that process, we get x squared minus 1. But then, because our g of x is inside that f of x, it goes into our f of x box, and that's our square root, and so we apply the square root, and we get the square root of x squared minus 1. And so think of it this way. Suppose I want f composed with g of 3. That's f of g of 3. F of g of 3 is 3 squared minus 1. 3 squared is 9 minus 1 is 8, so that's f of 8. And f of x is the square root of 8. And well, if you want, we could write that as 2 square roots of 2, or I would just leave it as the square root of 8. So when we get a 3, let me actually pick a different color, because I think that'll help us see it. I have 3 is our input, goes through g of x, and we get out 8. And it goes through f of x, and we get the square root of 8. And now if you want, we can think of it this way. I'm running out of space. I'm going to go to the next slide. I'll rewrite my functions, okay? We have f of x equals the square root of x, and g of x equals x squared minus 1. F composed with g of x is f of g of x. That's f of x squared minus 1. So what we can do is we can take that and substitute that in for every x. We get the square root of x squared minus 1. And so that's our algebraic method. And so f composed with g of 3 is just the square root of 3 squared minus 1. 3 squared minus 1 is the square root of 8. Now I haven't talked about the domain. We knew before with our combining functions, our sum, difference, product, and quotient, all of our x's that were in the domain of f and the domain of g. What ends up happening here is our domain is going to be, and let me write this in a different color, domain, are all x in the domain of g with g of x in the domain of f. And now g of x, our output, right, is often our y before we switch to function notation. Oh, that's not g, that's f. And so it's all x in the domain of g with range of g in the domain of f. What does that mean? So the domain of f here was, we'll write our domain and our range. Our domain is from 0 to infinity. And our range is also 0 to infinity, right? Because our square root graph looks like that, a little curvier. And then our x squared minus 1 looks like that, coming down here to -1. So our domain here is all reals, and our range is from -1 to infinity, because it goes all the way down to -1, but then it goes up to -infinity. So my question, what's the domain of f composed g of x? Well, if we look at this here, this is all x greater than 1. Right, because at 0 we get the square root of -1, which is undefined. So here we need x bigger than or equal to 1. And you're like, well, where would I get that from? Well, let me go to another slide. And so we have f of x, the square root of x, and g of x was what? It was x squared minus 1. And then I'm going to graph them both together now. And now we have our, so that's f of x, g of x. At 2, we're at 3. Looks something like that at g of x. And we care about x values where the range of g of x is in the domain of f. So we need, our domain of f is from 0 to positive infinity. And so our range of g between 0 and infinity happens between -infinity, so this side over here, all the way down to -1 inclusive, or 1 to positive infinity. So what does that mean? If we go back to our previous slide, we need not just x is bigger than 1, we can also have x less than or equal to -1. So the domain of f composed with g of x is this. From -infinity to -1, or 1 to positive infinity. And so finding the domain often is the most involved portion of evaluating composite functions. But let's say, let f of x equal 2x plus 1, and let g of x equals 2x squared minus 3. Evaluate f compose g at 2, and we don't have to only go one direction. G compose f at 2. Well, f compose g at 2 is f of g of 2. And so if we drew we have two options, right? We can evaluate g at 2 and then substitute that in. So here we can just say g of 2 is 2 times 2 squared minus 3, which is f of 2. 2 squared is 4 times 2 is 8 minus 3 is 5. We have f of 5. 2 times 5 plus 1. 2 times 5 is 10 plus 1 is 11. So that's one way we could do it. The other we'll use with g compose f of x. Well, here, I'm actually at 2, but I'll leave it x because we're going to find the general form. G composed f is now where we have g of f of x, and we substitute f of x into g of x. So now we have 2 times, and substitute this in for the x, 2x plus 1 squared minus 3. So g composed f of, what was it, negative 2? 2? G composed f, oh, it's right there. G composed f of 2 is 2 times 2 plus 1 squared minus 3. 2 times 2 is 4, plus 1 is 5. 5 squared is 25. Times 2 is 50, minus 3 is 47. And so we'll look at just a couple more examples of G compose F, right? Because we need not move in that singular direction. So here now we have x going into our function, f of x equal absolute value x plus 1. Going into our next function box, g of x equal 3x squared minus 1. Giving us an output. So let me write my x goes in here, and then it goes in here. So we have f of x, then g of x. So this is g compose f of x. So g of f of x. So that's g of absolute value of x plus 1, which is 3 times absolute value of x plus 1 squared minus 1. Well, an absolute value squared is always positive. But we'll leave it this way. G composed f of 2. Right, because if we want to, we could go 3x squared plus 2x plus 1 minus 1, and simplify that as 3x squared plus 6x plus 2. But we'll leave it like that. G composed f at 2 is 3 absolute value 2 plus 1 squared minus 1. 2 plus 1 is 3, squared is 9, times 3 is 27, minus 1 is 26. G compose F of -3, therefore is 3 absolute value, -3 plus 1, squared minus 1, -3 plus 1 is -2, squared is 4, times 3 is 12, minus 1 is 11. Ooh, we got through it. I'm going to do one more find the domain example. Find the domain of F compose G of X and find F compose G of X algebraically. Well, F of X is 1 over X minus 1. G of X is 1 over X. So remember, first and actually I'll use a different color. First, exclude X not in domain of F and G. Well, here in F, X can't equal 1, and here X can't equal 0. Then exclude any that make our final form improper. So exclude those that make F compose G undefined. You're like, well, how do you know what those are? Well, this is where we're going to find it algebraically. F compose G of X F compose G of X is going to be F of 1 over X. So that's 1 over X minus 1. And this denominator can't be 0. So what X value would make that denominator undefined? Well, it would be whenever, and I'll pick blue, whenever 1 over X minus 1 equals 1. No, when it equals 0. Add that 1 over, that's 1 over X equals 1, or an X equals 1. Well, in this case, 1 was already excluded because of the first term. But generally speaking, that won't always be the case. So our domain is from -infinity to 1, 1 to infinity. And F compose G of X was 1 over X minus 1. Let's do the same here for F of X equals 1 over X, and G of X equals 10 minus 5X. So first, X can't be 0, step 1. Then F of G of X is F of 10 minus 5X, which is 1 over 10 minus 5X. Well, 10 minus 5X can't equal 0, so if 10 equals 5X, X equals 2. And so now we exclude X equals 2. So F compose G of X equals 1 over 10 minus 5X. our domain is negative infinity to 2, union 2 to infinity. What happens if I plug a 2 in, right? So in my previous example, I said we had to exclude the term for the f, and then in both. And then here I said, well, exclude x equals 0, and this, and then I said we have to exclude x equals 2. So I'm going to go to the next slide. So we have f compose g of x equals 1 over 10 minus 5x. X can't equal 2. What about x equals 0? Because here we have 1 over 10 minus 5 times 0. It's 1/10. It certainly looks defined. What do you think? Pause and think for yourself. It looks to be defined. Let's go back to our definition. So, or even earlier than that. I said we need the x values where the range of g of x is the domain of f. That is our domain. So it's not that we exclude those in f and g and then exclude these. We only exclude those where the final version is undefined, because we only care about those x values of g that make that undefined. And if we would put, say, a 2 here, we end up with 0. It's not defined. But here we can include because we only care about where g of x is in the domain of f of x. And so the domain of f of x was whenever x wasn't 0. And so we only care about g of x doesn't equal 0, and g of x only equals 0 at 2. So to wrap that up, finding domain of g of f compose g of x. So it's the values of x that result in g of x, its range of g, in the domain of f of x. And we can find easily by algebraically finding f compose g of x and excluding x with f compose g of x undefined. So it doesn't matter if that x value would result in an undefined f or an undefined g, as long as in the final function, when simplified algebraically, it holds. So spend a little bit of time with combining functions and composite functions, And we're going to revisit composite functions in our next section on inverse functions.